So, good morning, class. Today is our third lecture day for CHM 121 Physical Chemistry 2 part of that class. And today we're looking at Henry's law and Raoult's law. Henry's law and Raoult's law. On Wednesday, I touched Henry's law a bit for you. And so we have to continue from where we stopped. So you can recall that the solubility of a solid and liquid are not affected by pressure. For solid and liquid, the solubility is not affected by pressure. If you can recall from Wednesday's lecture. And whereas solubility of a gas in any solvent is affected by pressure. Solubility of a gas in any solvent is affected by pressure. So for gas, solubility increases in direct proportion to its pressure over the solution. And this is what Henry's law is explaining. That solubility of gas increases in direct proportion to its pressure over the solution. So the relationship between pressure and the solubility of a gas is expressed by an equation known as Henry's law. And so this is what Henry's law says. Henry's law says that the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas over the solution at constant temperature. So temperature remains constant, it's not varied, you don't change the temperature. So if the temperature remains constant at a particular temperature, then the solubility is directly proportional to the partial pressure. So you can see the equation here, C for gas, that is the solubility of a gas, is directly proportional to the partial pressure. And when you replace the proportionality sign with an equal sign, then it becomes solubility of the gas, that is Cg, is equal to Henry's law constant, Henry's constant, times the pressure. So Kh is Henry's law constant, and the Pg is the pressure of the gas, while the Cg is the solubility of the particular gas in question. And so the solubility has a unit, molarity or moles per liter. Henry's law constant is often expressed as molarity per atmosphere. The atmosphere is the pressure. So the partial pressure of a gas is often expressed in atmosphere. So that's why you have the Henry's constant, law constant, as molarity per atmosphere, which shows the concentration per pressure. So when the partial pressure of the solute above a solution drops, if the partial pressure of the solid above the solution drops, the solubility of that gas in the solution also will drop to maintain an equilibrium. That means if you reduce the partial pressure of the solid above the solution, then the solubility will reduce. to balance up equilibrium. And also, if you increase the partial pressure of the gas, solubility will increase to maintain that equilibrium. So this can be used. The Henry's law can be used to calculate the molar solubility of a gas. This equation can be used to calculate the molar solubility of a gas. You can still use this equation depending on what is given to you to calculate the Henry's constants. And also, you can still use it to calculate the partial pressure depending on what you're given and what you're asked to do. So, still under Henry's law, we set it again clearly for you that the solubility of a gas depends, a gas in a liquid depends on temperature, depends on the partial pressure of the gas over the liquid, depends on the nature of the solvent, it depends on the nature of the gas. We're talking of depending on temperature, I mean at a particular temperature that you keep that system at that particular temperature. When you change the temperature to a different temperature, the solubility will change. So the most common solvent is water. So looking at this for carbonated beverages, carbonated beverages are an example of Henry's law in everyday's life. So the dissolved carbon dioxide stays in solution in a closed pop bottle or a can where the partial pressure of the carbon dioxide was set at a high value during bottling. It's during bottling that the partial pressure is set at a value that will help the carbon dioxide to be in solution. So when the can or bottle is opened, the partial pressure of carbon dioxide is much lower, and the dissolved carbon dioxide will gradually escape from the pop. So what this means, by the time you open the bottle, the partial pressure is reduced. So some of the gas will escape, and then the new partial pressure equilibrium will be established. This is now lowered, and so then the soda becomes flat. No longer like what it was when you had carbon dioxide dissolved in it. It becomes flat. So the loss of dissolved carbon dioxide will happen fast for a warm soda than a cold one. Remember that for gas, that solubility increases when the temperature reduces. So that's why the loss of carbon dioxide in a soda liquid will be fast when the soda is warm, because when it's warm, solubility is not encouraged. So solubility increases with decrease in temperature. And so with decrease in temperature with cold soda, just the rate of loss of carbon dioxide will be slow. So still making the Henry's law clearer to you, the concentration of dissolved gas depends on the partial pressure of the gas. The partial pressure controls the number of gas molecule collisions with the surface of the solution. So when you build more partial pressure, more gas will go in collision, more molecules will collide with each other and then go into solution. So if the partial pressure is doubled, the number of collisions with the surface will also double. So the increased number of collisions produce more dissolved gas. So we have an illustration here to show that if the pressure is doubled, then the concentration of the dissolved gas will also double. You see the first example there. See the first figure on the left that shows that low pressure equilibrium brings low concentration. So you see that where you have the two, let's say you have the gas up there and you have the liquid down. See the two layers, the gas layer up and the liquid down. So at low pressure, you can see how scattered the gas molecules are. But when you give more pressure, and you can see there that you have just two gas molecules going into the solution there, when you have low pressure equilibrium. Then when you double the pressure, you double the pressure equilibrium, you double the concentration. In the second figure there, you see where the pressure is applied more, double pressure is applied. You can see how the gas molecules are compacted more, and then they are brought more to contact with the solvent, to the solution molecules. And then you can see 4 molecules of the gas getting into the solution when the pressure is doubled. Unlike the other side, the one I showed you, the first one here, where pressure is half of what is here. So I believe this should be able to explain to you better what we're talking of in Henry's law. So let's look at an example here. The solubility of nitrogen gas in water at 25 degrees centigrade and 0.78 atmosphere pressure is 5.3 times 10 raised to power minus 4 molar. So if you have your biro, your paper, you can put it down and see. You can, or your calculator, yes, you can use it to calculate this. So follow up as we're going. Don't miss any of these examples of these calculations so that you'll be familiar with it, you have full understanding. Please mute yourselves. So at the end of the lecture, you will have time to ask questions. But for now, just mute yourselves and listen to me and follow all the steps. So using Henry's law constant for nitrogen now is given by C gas is equal to KH times P gas, where C gas is the solubility of the gas, KH is Henry's constant, and P gas is the pressure of the gas, the partial pressure of that gas. So now, you know from this equation, when you're calculating the solubility, you need Henry's constant. But in the problem that is given to you, the example given to you, you're not given Henry's constant. So the first thing you need to do is to find Henry's constant so that you can make use of it.
Hey, driver.
Can you please mute yourselves? Please mute yourselves. I don't want to force and mute you. Mute yourselves. So you can see that in the problem given to you, you're not given the Henry's constant, but you see that in the equation, you need Henry's constant to do the calculation. So the first thing you need to do is to calculate your Henry's constant. So you have everything here to calculate your Henry's constant. So from this calculation, your Henry's constant is your solubility divided by the partial pressure. And you've been given the solubility and the partial pressure. So when you divide it, you have your Henry's constant for nitrogen gas as 6.8 times 10 raised to power minus 4 moles per liter atmosphere. So now you have the Henry's constant for nitrogen gas. So the next thing you will do will be to calculate the solubility of nitrogen gas when the pressure is doubled. The pressure we have here is 0.78 atmosphere. So if you double that pressure, what pressure will you have? So you just multiply the 0.78 by 2, that is doubling it. And so with that, you now use what you have there to put into the equation, and then you will have this, you have the answer. The answer will give you 1.06 times 10 raised to power minus 3. I hope you understand the explanation. So you will use what you need is the Henry's constant from what was given to you initially. So you've been able to calculate your Henry's constant. That is the Henry's constant for nitrogen at any time. So you've been able to calculate it. So double the atmosphere, and then that's the pressure, the atmosphere. Double it, and then multiply it by the Henry's constant, which you have here. That is 0.78. You multiply it by 0.78 times 2. Multiply that by this Henry's constant, 6.8 times 10 raised to power minus 4. Then the answer you will obtain will be 1.06 times 10 raised to minus 3 molar. That is the solubility. So you can see it will double it when the pressure is doubled. So there's another example here. So solubility for nitrogen gas at 25 degrees centigrade and 1 atmosphere. This is the pressure is 1 atmosphere. So the solubility here is 6.8 times 10 raised to power 4 moles per liter, or molarity. So what is the concentration of nitrogen gas that is dissolved in water under atmospheric conditions? The partial pressure of nitrogen gas at the atmosphere is 0.78 atmosphere. So this is the solution. You still use that relationship, that equation for Henry's law. C is equal to Kp. So you're given the solubility here as 6.8 times 10 raised to power minus 4. You put it there, and then your K, that is the Henry's constant, you will use it, you use the K that you got before. So the Henry's, you put it there, K, Henry's constant, the P, the atmosphere, the pressure is 1. Since the pressure is 1, and you put in your solubility at 6.8 times 10 raised to power minus 4 is equal to K times pressure. Pressure is 1 atmosphere. So that means your Henry's constant is also equal to the same value as the solubility. So now you have your Henry's constant, you have that solubility at 1 atmosphere. So the solubility of nitrogen gas in water at 0.78 atmosphere now is solubility, is the Henry's constant multiplied by the partial pressure that is given to you as 0.78, and that gives you 5.3 times 10 raised to power minus 4. So that is your answer. You can see from here that that decrease in solubility is as a result of lowering the pressure from 1 atmosphere to 0.78 atmosphere. What I mean by that is, if you see the problem given to you in this example 2, that at 1 atmosphere, the solubility of nitrogen gas is 6.8 times 10 raised to power minus 4 molar. At 0.78 atmosphere, this is lower than 1 atmosphere. So definitely you expect the solubility to be lower than 6.8 times 10 raised to power minus 4. That's why it is lowered and reduced to 5.3 times 10 raised to power minus 4. I believe you understand this now. So now determine the quantity of carbon dioxide in 1 bottle of carbonated water if the pressure of 2.4 atmosphere is applied in the bottling process at 25 degrees Celsius. Given that the Henry's law constant of carbon dioxide in water is 29.76 molar per atmosphere at that 25 degrees centigrade. Well, the solution is already given to you here. Still using that formula, that equation, C is equal to kPa. So C is kPa. So you've been given the Henry's law constant as 29.76. So you substitute it there. Then the pressure at 2.4, substitute it there. So the solubility you have as 71.42 molar or moles per liter. So this is 71.42 moles per liter. That means 1 liter bottle of carbonated water contains 71.42 moles. 1 liter contains 71.42 moles of carbon dioxide. So now let's find the mass, the exact mass or grams of carbon dioxide that is put in there. So your mass, there's a relationship that you should know in calculating molarity or so, that mass is equal to number of moles times molar mass. You should know this formula, that mass is equal to number of moles times molar mass. So you've calculated the number of moles of carbon dioxide there as 71.42 moles in 1 liter. So the molar mass of carbon dioxide is 44 grams per mole. 44 grams in 1 mole. So 1 mole of carbon dioxide has 44 grams. That is the molar mass. So now the mass that you want to find out exactly how much grams, how many grams have been added. So you now get that as 3,142.66 grams, which is same thing as 3.1 kg. So you've been able to calculate the exact measurement, exact grams, exact amount of carbon dioxide that was added. So that's how the solution to that problem is. I want to complete the lecture first before we go back to that, but I want to believe that you understand it because I've taken time to explain it to you. So note this about Henry's law. Note the following about Henry's law, that Henry's law only works if the molecules are at equilibrium. It works if the molecules are at equilibrium. And we will see that. I'm going to explain more, even apart from what you have seen before. And also note that Henry's law does not work for gases at high pressure. Doesn't work for gases at high pressure. For example, nitrogen gas at high pressure becomes very soluble and harmful when in the body, in the blood supply. So, so we don't use Henry's law for very high gases at very high pressure. Then Henry's law does not work if there's a chemical reaction between the solids and the solvent. For example, if you use hydrogen chloride gas inside water, Henry's law does not work for this because there's a dissociation there that is going on. The HCl will dissociate in water, it will dissociate into hydrogen ion and chlorine ions in solution. And this is a strong acid. So where a chemical reaction takes place and something is formed, you don't use Henry's law. It doesn't work for such situations. It works only where there's no chemical reaction. So how does this always fit? Let us say this. As concentrations and partial pressures increase, deviations from Henry's law become noticeable. Like I've told you that Henry's law does not work where the partial pressure is very too high and the concentrations become so high, so it doesn't work. So with this, the behavior is very similar to behavior of gases. This behavior is very similar to the behavior of gases, which are found to deviate from the ideal law. So gases that deviate from ideal gas law, the same behavior is what we see in Henry's law, gases that obey Henry's law. So this behavior is very similar to the behavior of gases, which are found to deviate from the ideal gas law as pressures increase and temperatures decrease. So for this reason, solutions which are found to obey Henry's law are sometimes called dilute solutions. So it's only dilute solutions that can obey Henry's law. Once it becomes highly concentrated with high pressure and so on, it doesn't obey Henry's law any longer. So now let's look at Raoult's law, an ideal mixture of liquid. We'll look at Raoult's law and we'll look at ideal mixture of liquids. What are ideal mixtures? An ideal mixture is the one that obeys Raoult's law. We will look at Raoult's law. What do we mean? What is Raoult's law? We'll look at it also. So an ideal mixture is the one which obeys Raoult's law. But let's look at the characteristics of an ideal mixture first, before we actually start stating Raoult's law. Let's first of all know what are the characteristics of an ideal mixture. So let's look at examples of ideal mixtures here. There is actually no such thing as an ideal mixture. In real sense, there is actually no such thing as an ideal mixture, but there are some liquid mixtures that get fairly close to being ideal. Very, very close to being ideal. So these are mixtures of two very closely similar substances. Two very close similar substances. You will see the explanation soon. So when we have such, we can assume it to be, we'll take it to be ideal. So we'll see examples here like hexane and heptane. If you mix hexane and heptane, of course, you know they're both nonpolar. And then also, these are non-polar we're looking at. And also, if you mix benzene and methylbenzene, you mix propan 1-ol and propan 2-ol. So you see that these are situations when we're looking at as ideal. So mixing two mixtures that are of very close, similar substances. So let's look at it here now. What we're still looking at is the characteristics of ideal mixtures. You will have to understand first the characteristics of ideal mixtures before we get to stating Raoult's law, so that it will be very clear to you. And so now, let's look at these two ideal mixtures. These two molecules, two solutions that we want to mix. So look at the one that is having blue molecules, and the other one on the right that is having red molecules. Say, for instance, that we've taken examples here. So hexane and heptane. Let's say that the one with blue molecules is hexane, the one with red molecules is heptane. So let's look at the one with blue molecules. That is the solution itself without mixing. These are two solutions without mixing. We'll look at them separately first, and then we will look at them when they are mixed. What happens in a situation of an ideal mixture? So in a pure liquid, some of the more energetic molecules have enough energy to overcome the intermolecular attractions, and they escape from the surface to form a vapor. So in a liquid, you will have intermolecular attractions, that molecules attracting each other within the solution, within the liquid, and keeping it in liquid form. So the molecules are staying together to be in liquid form. They're not released. So there's something that is keeping them together. There is an intermolecular attraction or force that is keeping the molecules together for them to remain in liquid form. So, but some of the molecules towards the surface, sometimes they're so energetic that they can manage to escape and go into vapor. So the smaller the intermolecular force, the more molecules will be able to escape at any particular temperature. At any particular temperature. The smaller the force that is holding the two molecules, the similar molecules together in a solution, the more the tendency of the molecules to escape. So that means the molecular attraction between the molecules is weak, not strong enough to hold the molecules down in solution. So when it is weak, when it's low, when it's small, it's weak. So the molecules manage to escape. And you can see here, in this blue, you can see here 4 molecules are able to escape. We want to use numbers like this so that we'll be able to understand well. And the similar thing is happening also for the other liquid. Let's say heptane. The first one I said, let's take it, let's say it's hexane. And this other one red, let's say it's heptane. So for this, it's the same thing that is happening. So if the second liquid, the same thing is true. So at any particular temperature, a certain portion of the molecules will have enough energy to leave the surface. So just have that in mind for now. So let's go and see the situation. What happens when the solutions are mixed? So now, when the two solutions or the two liquids are mixed to form this solution, this is what happens. So you still see 2 molecules or 4 molecules escaping. You might think that the diagram shows only half as many of each molecule escaping. because you see 4 molecules escaping. You see, out of the 4, you see 2 red and 2 blue. But it's not that we're showing half of it escaping. The proportion of each escaping is still the same. What happens here is that the mixture, we just use 50-50 mixture of the 2 liquids. The liquid you saw before, we're not mixing all. So this is 100%, this is 100%, or this is how it is. So we just take 50 of this and 50 of this to make it 100. That is what you see here in this slide, 50-50 of it. So that means that there are only half as many of each sort of molecule on the surface as in the pure liquid. So if the proportion of each escaping stays the same, obviously only half as many will escape in any given time. I hope you're following me. Only half as many will escape at any given time. You know, we have the other 100 here, 100 here. So 4 escaped in 100 of liquid here, 4 escaped in this 100 of liquid, the other liquid. So now, when we now take half of this liquid and half of this liquid and put together to make that 100, it means half of this one is escaping and half of the other one is escaping. So the proportion of escaping still remains the same. So it means if you have put 100, 100 to put it all together, it means 4 of the other one will still escape and 4 of this other red one will still escape. So if the red molecules still have the same tendency to escape as before, that must mean that the intermolecular forces between 2 red molecules must be exactly the same as the intermolecular forces between a red and a blue molecule. So it means the intermolecular forces that are keeping them together still must remain the same. So if the forces were any different, then the tendency to escape will also change. I hope you're following me. So now, exactly the same thing is true of the forces between the 2 blue molecules and the forces between the blue and red molecule. They must all be the same. Otherwise, the blue ones will have a different tendency to escape than the red ones. From what I've shown you here, the blue and the red, each of them have same tendency to escape. Each same proportion escaped because it is the same type of the same strength of intermolecular forces that is holding them in place. So in the mixture here, as you see, there are intermolecular forces between blue molecules, between red molecules, and between blue and red. So in an ideal mixture, the intermolecular forces between the 2 different molecules must be the same as that between similar molecules. So intermolecular forces must remain the same so that the tendency of any of the molecules to escape will remain the same. So what I mean there is that if you follow the logic of this through, follow it through what I just explained to you, it means the intermolecular attractions between 2 red molecules and 2 blue molecules, either the one between 2 red molecules will be the same as the one between 2 blue molecules, will be the same as the one between a red and a blue molecule. All the intermolecular attractions must remain the same if the mixture has to be ideal. So that's a key characteristic of an ideal mixture, that all the attractions, intermolecular attractions inside the liquid must remain the same. And so the escape tendency for any of the molecules there also remains the same. This is an ideal mixture. So this is why mixtures like hexane and heptane get close to ideal behavior. They are similarly sized molecules, and so they have similar sized van der Waals attraction between them. So the force between the molecules is called van der Waals attraction. So since the size of the molecules are the same, so the van der Waals attractions between them that will hold the two different molecules together will still remain the same as that is holding each similar molecules together. And so, however, they obviously aren't identical. We know that they're not identical. But though they get very close to being ideal, they actually are not ideal, but they're quite close to being ideal. So for the purpose of this topic, we want to look at them as being ideal enough, good enough as ideal. So that's what we see it to be. And I think I will stop the lecture here. The Raoult's law, I've not stated it for you yet, but with the understanding that you have here, you'll be able to understand Raoult's law, because we're going to use an ideal mixture to explain Raoult's law for you. So that's the end of this lecture. I need somebody, if you have question, you can ask. So somebody should raise hand and ask question. Raise hand and ask question. You have anything that is not clear to you? Okay, Rokiba, ask your question. On mute, okay. Yes, Rokiba, I'm listening to you. Rokiba, we're not hearing you. Rokiba, not hearing you. You're not talking. Does any other person have question to ask? Obinna, Timothy.
Why is everybody sit there? I don't hear me whenever I'm doing.
Okay, Rokiba, I think I'm hearing you now. Rokiba, go ahead and speak. We're not here. I'm hearing you now. Speak. Rokiba, it's only when you were complaining that we heard you, and when you're speaking, we cannot hear. Oh, I still cannot hear you, Rokiba. Maybe you come back. Timothy, can you ask your question?
Good morning, ma.
Good morning.
Yes, ma. When you are using you are explaining Henry's law, that
Yes.
is C equals to KP.
Yes.
In the case where you are giving, you give us a class assessment of using carbonated drink. In the case where in carbonated drink, ma, we have H2CO3. That is the whole mixture. Now, how can now if we have that is reacting CO2 with water to have that. Now, if we're having HNO3 that is gotten from H2O plus NO2, can we still do the same thing by just ignoring the hydrogen component of the mixture and focus on the nitrogen 4 oxide?
No, you heard what I said, that Henry's law, because the carbon dioxide you have there, okay, you're telling me that it's forming a compound.
Yes, ma. When it's inside the water, it's forming H2CO3. As carbonic acid, ma.
No. No, it's not so. The other one, then can you, it's not. So it's actually, yes, it's so, but you cannot use it. This one is different. The nitrogen case, which you're going to have some ions, going to, like we use a case of HCl. So it's different. So in this case, you still have your gas there. Yes, it's mixed, but it will not work for nitrogen because, like I gave you an example there of the HCl. Let me go back to this slide. So those ions, it will dissociate and form those ions. In that case of the the one for nitrogen, so it will dissociate and form some ions, and it will not work. It will not work for that. It will be working for the carbon dioxide.
Okay, ma'am.
Any other question? Rokiba, we don't know why we cannot hear you. Okay, so I think so far everybody is okay with the lecture. It's clear enough. And so on Monday, we'll continue. I think then we'll be able to state Raoult's law and relate it with ideal mixture and do some more calculations. But I think so far, for the 3 lectures, I believe strongly that if you're given a test or anything, questions, you'll be able to answer them well because I believe it's quite clear to you. So we'll see again on Monday. I believe can somebody let me know if you saw the lecture of Wednesday on LMS? Did anybody see it? Somebody should unmute and answer me. We're about closing the lecture. Somebody should unmute and answer me. Did anybody see the lecture of Wednesday on the LMS? Favor, did you see? Favor?
Yes, ma'am.
Did you see the lecture on LMS?
Yes, ma'am.
Okay, I believe every other person saw. So today, immediately after this, I'm going to send today's one to you. So thank you and goodbye. We'll see you next on Monday by 9 a.m. Bye.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
Okay.
Thank you very much.
Thank you also. But I want to tell your colleagues that they should be attending class because today's class is so poor. I have just about 68 people in the class today. And how many of you are supposed to be there? It's so poor. And you can see the lectures that it's somebody that is in the class that will understand it better and ask questions. Somebody that is not in the class will just be struggling. So encourage your colleagues to try and attend the class. Even though we are giving the notes, but it's good to also be in the class. Although you can see, but we'll be checking attendance also. So tell them, tell your colleagues, we'll be checking attendance. The attendance matters a lot. Thank you. Bye.